We're now going to extend our results from the one-period binomial model to the multi-period binomial model. We'll see that our results from the one-period binomial model actually extend very easily to the multi-period model. So let's get started. Here's a three-period binomial model. It's actually the same three-period binomial model that we saw a while ago when we had our overview of option pricing. We start off with a stock price of S0 equals $100. We have a gross risk-free rate of R equals 1.01 per period. We assume that in each period the stock price goes up by a factor of U or it falls by a factor of D. So U is equal to 1.07, so stock price goes up by a factor of U to 107, or it falls down to 93.46. Now the true probability of an up move is P, and the true probability of a down move is 1 minus P. But we also saw in the last module that P and 1 minus P don't matter when it comes to pricing an option. As long as, in fact, and this is a subtle point, as long as P and 1 minus P are greater than 0, and there's no arbitrage, we determined that there were Q and 1 minus Q also greater than 0. These guys are called the risk-neutral probabilities, and we saw that we can use these probabilities to compute option prices. For example, in our one-period model, we saw that we can compute the price of a derivative as being equal to 1 over R times the expected value using these risk-neutral probabilities of the payoff of the derivative at time 1. Okay, so we're now in our three-period binomial model. We want to be able to price options in the three-period binomial model. And we can easily do that using our results from the one-period case. Because the central observation we want to make is this multi-period, or in this case three-period binomial model, is really just a series of one-period models spliced together. So for example, here's a one-period model. Here's another one-period model. And here's another one-period model. So in fact, from t equals 2 to t equals 3, there are 3 different one-period models, only one of which will actually occur, but there are 3 possible one-period models. Likewise, at t equals 1, there are 2 possible one-period models. There's this model, and there's this one-period model. And at t equals 0, there's only one one-period model, and it's this one. So in fact, we see we've got 6 different one-period models in this three-period binomial model. And what we can do is we can use our results for the one-period model that we developed in the last module on each of these 6 one-period models. So in fact, that's what we will do. Okay? So what we have is we saw that if there's no arbitrage in the one-period model, we know there are probabilities Q and 1 minus Q. These are the risk-neutral probabilities that we can use to price an option in this one-period model. Well, the same risk-neutral probabilities will occur or can be used here and here, and likewise there and there. Remember, each of these one-period models is essentially identical. The stock price goes up by a factor of U or it falls by a factor of D. It's the same U and D in each of these one-period models. It's also the same gross risk-free rate R in each of these models. So in fact, they'll have the same risk-neutral probabilities. U is equal to R minus D over U minus D. So in fact, since R, D, and U are the same for all of the one-period models, all of the one-period models have the same risk-neutral probabilities. Q, 1 minus Q, Q1 minus Q, Q1 minus Q. And indeed, it's true also at time t equals 1. Q, 1 minus Q. And of course, these are the true probabilities. Well, let's erase them. And let's replace them with the risk-neutral probabilities Q and 1 minus Q. So in fact, this three-period binomial model can be thought of as being 6 separate one-period models. If each of these one-period models are arbitrage-free, and we recall that will occur if D is less than R is less than U, then we can compute risk-neutral probabilities for each of the one-period probabilities, and then we can construct probabilities for the multi-period model by multiplying these one-period probabilities appropriately. Suppose, for example, I want to compute some risk-neutral probabilities in this three-period binomial model. How can I do that? Well, let's create some space here and let's get rid of this stuff. Okay. let's compute the probability, the risk-neutral probabilities, let's call them Q, of arriving at each of these terminal security prices. So how about this point here? What is the risk-neutral probability of the stock price being equal to 122.5? Well, the only way the stock price can equal 122.5 is if the stock price goes up in each period. It has to go up in every period. The probability of it going up in every period is Q times Q times Q, and that's Q cubed. How about at this point here? What is the risk-neutral probability of the stock price being equal to 107 at time t equals 3? Well, in this case, it's actually going to be 3 times Q squared times 1 minus Q. Now, how do I know that? Well, let's think about it. There are actually 3 ways to get to 107. One way is for the stock price to fall initially, and then to have 2 periods where it goes up. A second way is for the stock price to have 2 periods up, followed by 1 period down. And a third way is for the stock price to go up, then to go down, and then to go up again. So there's 3 such paths through the model where the security price at time t equals 3 can end up at 107. Each of those paths requires 2 up moves, which occurs with probability Q squared, and 1 down move, which occurs with probability 1 minus Q. So we get Q squared times 1 minus Q, and there are 3 such paths, so we get 3Q squared 1 minus Q. Okay, it's the same for 93.46. There are 3 ways for the security price to get to 93.46. It can go up and then have 2 down moves, it can have 2 down moves and then 1 up move, or it can have a down move, an up move, and then a down move. So in fact, this occurs with probability 3Q times 1 minus Q squared. We have 1 minus Q squared now because we need 2 down moves, and the down move occurs with probability 1 minus Q. Finally, the stock price can be 81.63 only if we have 3 down moves in a row, and that occurs with probability 1 minus Q cubed. Okay? You might recognize these probabilities as being the binomial probabilities. Okay, so the binomial probabilities will say that the probability will be n choose r times q to the r 1 minus q to the n minus r. In this case, n is equal to 3, and r is the number of up moves required. So if r equals 3, then we must have 3 up moves and we get q cubed. If r equals 1, then we have 3 choose 1 equals 3, and we get this number here, and so on. So now suppose we want to price a European call option in our 3-period binomial model. We're going to assume the strike is $100, and therefore the payoff of the option at time t equals 3 is given to us here. It's 0 and 0 in the bottom 2 nodes. This is because the strike is $100, which is greater than the stock price at these nodes, so you wouldn't exercise and you would receive 0. If the stock price ends up at 107, you would exercise. You'd get 107 minus 100, which is $7. Likewise, up here, you would receive $22.5. And now what we want to do is figure out how much is this option worth at time t equals 0. In other words, what's the fair value or arbitrage-free value of this option? Well, we can do this simply by working backwards using what we know about the 1-period model. So we know how to price options in a 1-period model. We saw this in the last module. We're going to do this here as well. So what we can do is we can start at time t equals 3, okay, and we're going to work backwards. From t equals 3. So what we can do is we can actually start with this 1-period model here. So let's take a look at this 1-period model and just figure out how much is this derivative security worth at this node here. This is a 1-period model which pays off 7 at this node, 22.5 at this node. We can compute the fair value of the security at this node. We can do that using our 1-period knowledge. We can do the exact same for this node, Okay, we can treat this as a one-period model, compute the fair value at this node, and also compute the fair value at this node. Okay, so by working backwards now, we can assume we know the option price at this node, and this node. And now we can do the exact same thing. We can now go from t equals 2 back to t equals 1. In this case, we've got two one-period models. Here's one of them. We know how much the option price is worth there. We know how much it's worth here. So we can figure out how much it's worth here, again, using our results from the one-period theory. Likewise, in the one-period model here, we can do the same thing. We know how much the option is worth at this node. We know how much it's worth at this node. It's already calculated. And we can use our one-period knowledge to figure out its value at this node. Finally, we can go from t equals 1 to t equals 0. And again, we want to compute the value of a derivative security with a payoff of this quantity at this node and this quantity at this node. And we can actually compute the fair value of this, again using the risk-neutral probabilities, to compute its fair value here, which we would call C0. So that's all you have to do. Right? We can splice our one-period models together. They're all arbitrage-free, as we said, because D is less than or is less than U. So there are risk-neutral probabilities in each of these one-period models. So what we can do is just work backwards, starting off with the final value of the option at t equals 3, figure out how much it's worth at the nodes at t equals 2, using our one-period theory, going from t equals 2 back to t equals 1, again using our one-period knowledge, and from t equals 1 back to t equals 0. And here are the calculations. So I haven't actually done the calculations here, but there is a spreadsheet that you can download with this module, and in the spreadsheet there'll be a particular worksheet which will actually have these calculations, as well as the formulas inside the cells which will do these calculations for you. So what you'll see is we're actually calculating these quantities according to the one-period model. So for example, let's take a look at this one-period model here. I know that the 15.48 over here is equal to 1 over R times Q of 22.5. So Q times 22.5 plus 1 minus Q times 7. This comes from our one-period theory, and of course Q is the risk-neutral probability of an up move. It's equal to R minus D over U minus D. And of course in this case, U is equal to 1.07, D is 1 over U, and R was equal to 1.01. So you can actually check these calculations in the spreadsheet. If you like, you can have the spreadsheet open while you're going through this module, and you'll see the formulas in each of the cells showing these calculations. So what we're doing is we're working backwards. So the cell here at this point in the spreadsheet will have exactly this formula here. Likewise, except it won't have 22.5 and 7, it will just refer to the cells containing 22.5 and 7, and it will be the same formula repeated throughout the spreadsheet. So that's how we compute the value of the option, and its fair value at time 0 is 6.57. And it's important to keep in mind that this is the arbitrage-free value of the option. The way we calculate this value is by using our one-period knowledge and working backwards one period at a time. But in fact, there is a faster way to do it. We can use what we did in the previous slide where we calculated these risk-neutral probabilities. Okay, so these are our risk-neutral probabilities. You can easily check that doing this backwards calculation, working backwards one period at a time, is actually the same thing as doing it all in one shot. So instead of doing a calculation coming back from t equals 3 to t equals 2 to t equals 1 to t equals 0, I can do it as just one calculation, okay, where the call price at time 0 C0 equals 1 over R cubed. So this is our discount factor. It's cubed because there's 3 periods. And it's the expected payoff of the option, which is ST minus 100, and the maximum of that in 0, under these risk-neutral probabilities here. So I can do it in one shot. So basically, working backwards one period at a time, you can check is it the exact same thing as doing it all as just one calculation like this. Okay? This is risk-neutral pricing in the binomial model. It avoids having to calculate the price at every node. And by the way, you can compute any derivative security in this model this way. You can compute the payoffs here at t equals 3 and use risk-neutral pricing in one shot like this. So for example, let's create some space here. So, okay. Suppose I want to compute a derivative security which has payoffs C, let's call it, okay, so let's call it C of 122.5. So this is the underlying security price at this node. C of 107, C of 93.46, and C of 81.63. Okay, so this could be the derivative payoff C3. There's some value at time t equals 3, and its value depends on the security price at t equals 3. So it could be a call option, a put option, or some other funky security. Then I can calculate this price as 1 over r cubed times the expected value using these risk-neutral probabilities of C3. Okay, and it's exactly the same argument we use for the one-period model. I could work backwards one step at a time to compute the value at each of these 3 nodes. Once I have those 3 nodes, I can work backwards to these 2 nodes. And once I have the value at these 2 nodes, I can work backwards to get the value here. Or I can do all of that in one shot via this calculation here. The spreadsheet does it by working backwards one period at a time, and you can see the formulas in there and confirm that all we're using are the one-period risk-neutral pricing formulas. Okay. Another question that arises is down here. How would you find a replicating strategy? We'll address this question as well as defining what a replicating strategy means in another module that we'll see very shortly.